So on behalf of the group, I would like to introduce Professor Richard Elliott. Professor Elliott graduated at Christopher Newport University, where he received his bachelor's degree in math and chemistry, a double major. He then received his master's degree in chemical engineering at Virginia Tech. And finally, he got his PhD, also in chemical engineering, from Penn State University. Professor Elliott is currently a professor emeritus at the University of Akron, Ohio, United States. He teaches several chemical engineering courses like Introductory Thermodynamics, Graduate Thermodynamics, Advanced Thermodynamics, and Material Science. He's the co-author of two well-known books. The first one, Introductory Chemical Engineering Thermodynamics, and the second one, The Properties of Gases and Liquids, which is a reference book to chemical process design engineers. Among his research interests, we can highlight thermodynamics of hydrogen bonding, molecular simulations, perturbation theory and integral equation theory, experimental phase equilibrium measurements, chemical reaction engineering, supercritical fluid processing, and well, several others, which I may not read because I have limited time. So in advance, I would like to thank very much Professor Elliott. And I would like to say that the stage is yours. I mean, the screen share is yours.
Okay, well, let's see. Now I have to figure out how to switch over from full screen. Oh, here we go. And then I have to share my screen, I think.
Yes, please.
Yes.
So I think, is my screen now showing?
Not yet.
Huh.
Not yet.
Okay, so now let me see what I have to do. Oh, I didn't push the share button.
Now it's okay.
Okay. So I think I'll just leave it. Oh, okay. But so these pictures are showing up on my side, but I guess I can work around them. Are they showing up? Are they blocking access to the content on the screen for you?
I can see everything, I think.
Okay, so well, let me just see something here. For you, you can read this DFT ... even when I'm in full screen mode.
Yep.
Yes.
Okay. All right then. We'll just keep going that way. All right, I'm gonna have to put my glasses back on now. So I picked a topic for this introduction that is maybe a little bit simpler than the average. And I wanted to do that because for starters, we need to get to know each other better. And especially with 48 people, there might be some diversity in the crowd. And so I think this is a topic that everybody can understand and appreciate. At the same time, if you're interested in more advanced topics, we will gently introduce those and touch on those topics. And those topics include starting with the ESD, then moving to SAFT, and then some perturbation theory, and a concept that I refer to as renormalization or recursion. Essentially, if you take the van der Waals repulsive contribution for the equation of state, write it as Z is equal to 1 divided by 1 minus B times rho. Think about that for a second. Now expand that in powers of density, and you'll see that you get 1 plus B rho squared plus B rho cubed plus B rho to the 4th power. It's just a series like that. And I guess I might as well go ahead and simplify that a little bit. Whenever I talk about this B, which is the van der Waals volume of a molecule, times the density, which is rho, those two things go together, right? Because the volume times the density is dimensionless number. That dimensionless number is the packing fraction. So the reason that the van der Waals Paul's equation is going to infinity for the pressure at 1 minus V rho, in other words, where the packing fraction is equal to 1, is because you can't put more molecules in than when the volume is completely packed full. That's pretty simple, right? So, but then if you divide that term, 1 over 1 minus eta, in a series of eta, you get an infinite series. So this infinite Taylor series is actually completely characterized by a relatively simple formula that is a recursion, 1 over 1 minus eta. And so my perspective on this is there are a lot more kinds of recursions like that are out there, that when we characterize those recursions, what we've got is a perturbation series of the Helmholtz energy in terms of temperature and packing fraction. But there are underlying recursions and renormalizations in that perturbation series that if we could extract those and put them in a more compact renormalized form, then we would have a much better physical understanding and a much more practical engineering equation. So that's what I mean by recursion and renormalization. The polymer limit, this is when your chain length goes to infinity. And that's something that comes up in the SAFT perspective pretty quickly. The prism theory is an integral equation theory, polymer reference interaction site model, that allows us access to that polymer limit in a very detailed molecular way, without having to do molecular simulations. And then density functional theory is recognizes that the density between a liquid and a vapor interface is actually a smooth function. So we need to know something about that Helmholtz energy at all densities in between the vapor and the liquid in order to characterize the interface properties. This one example of this accessing the inaccessible would be helium dissolved in 3-ethyl heptane. You'll see why I chose that particular molecule at a packing fraction of 0.61. Well, hopefully you know that spherical molecules, when you get to a packing fraction of 0.494, they crystallize into a face-centered cubic solid. So you can't study spherical molecules, which helium is, beyond a packing fraction of really 0.4, because if you're starting to get close to that crystallization point, well, yeah, okay, let's say you could go to 0.494. Let's say 0.49. Okay, but that's nowhere near 0.61. So if we wanted to understand how the helium is performing as a molecule inside as a Henry's law constants, for example, in 3-ethyl heptane at 0.61 packing fraction, we have no way of knowing what that is, except maybe by molecular simulation. We can simulate that. And then what is our theory going to be that we can use as a practical engineering tool? Because molecular simulation isn't really going to fit in a process simulator anytime soon. So those are some ideas that I wanted to get across in the course of this discussion, and so hopefully we can grasp the topics of this relatively simple subject, and then if you have more questions, we can get to those later on. So when I presented this at the AICHE meeting last fall, it was actually only 20 minutes long, but I'm already like 10 minutes in just with the introduction. So I'm going to probably extend it a little bit like that, because we're in a little less time constrained fashion here, and so I'll stop and kind of introduce some things that would be digressions in a normal presentation, but then I'm hoping that this particular research group may find interesting. So let's start with some definitions of terms. What do I mean by a systematic development? I think you'll see as I go through the outline how that systematic approach, what my perspective is on that. What is artifact-free? Well, the very next slide, I'll define what that means. The ESD equation is a E is for Elliott, in case you were wondering. Suresh was a grad student of mine. Donahue is a professor at Johns Hopkins, and he had developed something called APACT theory, which is associating perturbed anisotropic chain theory. And so I looked at that theory, and the first A in APACT was for associating. He had a different approach to doing that than what they were doing in SAFT. And so I wanted to leverage that theory. But I wanted to keep the equation of state cubic because my perspective was, looks like industry only cares about cubic equations, but we can still have the cubic equation be fairly realistic in terms of the qualitative representation of what's really going on in terms of molecular simulation. Well, later on, and you can see this in the Elliott-Lira second edition in chapter 19, we found that we could rearrange the ESD equation, and it is exactly a SAFT equation of state. Everything is perfectly consistent. Chapman has recently been working on something similar, actually, a cubic version of SAFT. And his version, if you look at it, is more like a kind of a Frankenstein's monster, of things pulled together from different places. In the ESC equation, say we do all that, but it's all really just completely self-consistent. It's just based on a particular assumption about the radial distribution function of a hard sphere fluid. And what we're going to see, well, you could ask, since it's cubic, it's inherently artifact-free. So if what we want is an artifact-free SAFT EOS, and an argument could be made that we're done. As soon as we understand the ESD equation, yep, we got an artifact-free SAFT equation of state. But very quickly you're going to see that the agreement between ESD equation of state and the molecular simulation results is not so good, especially at those higher packing fractions that I was alluding to earlier. So now, let's get systematic about this. Can we generalize or slightly alter the ESD equation of state so that it's still cubic, but maybe it does a little better job of satisfying the molecular simulation results, and we have to focus on some particular kind of molecules. Let's pick the inalkanes. So we'll call this the cubic SAFT A equation, because every SAFT equation needs some modifier letters. And so we can call it the SAFT alkane equation, and then it would be artifact-free, and it would still be better agreement with the molecular simulations. That would be a start. But it turns out you're still limited in how accurately you can agree with the molecular simulation results. So if the problem is a repulsive term, what would happen if we got rid of the cubic constraint and made it a more realistic repulsive term? Could we still be artifact-free? It turns out we can. But then we lose accuracy with respect to the first order perturbation contribution in this Taylor series expansion. Well, could we generalize this first order term? Because that's a very, very important term to get your vapor pressures right and all your thermodynamic properties right. So we need to be able to generalize that. Turns out that's easy to do, and there's not a problem. What about the second order contribution? That is where the problem comes in. And I hope that you'll come to understand why that problem is there, why it's significant, and why this problem is never quite done. Okay, so let's go to the next slide, and that only took 6 minutes. All right, what's an artifact? There's a paper by Nayef Al-Saifi that is very interesting, I think, and he provides this method of mapping out different equations of state and the artifacts that they exhibit. So correct physical behavior is illustrated here, where we're plotting volume on the y-axis and temperature on the x-axis. And so you see it should just be a simple van der Waals loop. But if you look at the various forms of the SAFT equation, they're a lot more complicated. And so the most popular SAFT equation these days is this PC SAFT equation. And so I'll focus on that one for a lot of my examples. Hopefully, probably you've done some calculations yourself with the PC SAFT equation and you are familiar with it. So what we're plotting here in terms of the artifacts is the identification of multiple liquid roots, where those in volume, where those roots are as a function of temperature at a constant pressure. And so to show you how you could easily identify where those points are and then create the bifurcation diagram, I've made a plot here of a dimensionless pressure. So this is V, the van der Waals V, times the pressure divided by the gas constant, the temperature. If you think about this, this is a dimensionless pressure. So it's just a little bit more convenient than pressure. And you can calculate this thing by just taking eta, the thing I talked to you about before, and multiplying it by Z, the compressibility factor, PV over RT. So really easy thing to calculate really quickly. So if we plot that, you probably can't see it down in here, but the pressure does go positive at first. It has to do that. Then it goes negative. And so here, just around here, we have a van der Waals loop. But wait, there's more. And now we have another van der Waals loop right here in the middle. But wait, there's more. If I was to plot it, you would see it goes up, comes down, and we have another van der Waals loop here. So we have 3 van der Waals loops in the PC SAFT equation at 6.2 kelvins. And I think this was propane. At 85 kelvins, this is the more typical behavior. In fact, this is considered the right behavior for PC SAFT. And what you see is it has 2 van der Waals loops, which is still 1 van der Waals loop too many. And so PC SAFT evidently has the protocol of always choosing this intermediate, this middle root as the valid root for its so-called liquid root. If you want to check the conditions of my calculations, they're all here. Well, these kinds of excess roots, if you're trying to write a robust process simulator or a flow field simulator for an oil reservoir, you need to be able to do things very quickly and very reliably. And when these excess roots start popping up, that's just a real big problem when you want to get the right answer all the time. Either, well, to be reliable about it, you have to sacrifice some speed so that you calculate all the roots, sort them all out, and only use the right one. If you wanted to map out a global phase diagram, which is a similar problem, then to be honest, your diagram ought to include the bifurcation diagram like Al-Saifi did. And then that's ugly. So, because those global phase diagrams, they make my eyes cross anyway. So another problem is accessing the inaccessible. I talked about this one before. And then I touched on this a little bit, the idea that we need to know the density. We need to know the properties all the way from the liquid density to the vapor density. And here what we're looking at is a vapor-liquid interface of hexanol dissolved in water. And you can see there's a lot of different densities floating around here. What I've tried to show you is that this density of the hydroxyl group is going to be facing inward towards the liquid water phase because the hydrogen bonding wants to mix with the water. Whereas the methyl group doesn't care for that. In fact, it's repelled by that, by the hydrophobic effect. And therefore, it will squeeze over towards the vapor phase. The ability to resolve these two separate density profiles of one molecule is a relatively recent development. We published on it a while ago, and it was a development by Bymaster and Chapman that laid the groundwork for being able to do that. So you can see that our lines are the theory and the points are the simulations, and we do get those two different density profiles. What's important about that is interfacial properties are really important for designing oil floods with water, especially, and also in the cosmetic industry. I don't know if you can imagine two more different industries. And so everything in between is also impacted by these interfacial properties. So for product designs of very many diverse flavors, these interfacial properties are very interesting. And the important thing is we need to know, in order to know what these interfacial properties are, we need to know exactly what the thermodynamics are at every density in between the vapor and the liquid. And they have to be right, or our theory will be wrong. So let's go back and let's think about that. Do you think this theory is right? Not. It's got all these weird things going on that couldn't possibly physically be happening. So we need to get that right in order to make sincere progress and systematic progress on the interfacial properties. So now let's talk about the ESD equation and how it sort of satisfies the overall constraint of a artifact-free cubic equation of state. So if we look at our Helmholtz free energy, we can see a couple of different renormalizations here. This one with 1 minus 1.9 eta, that's very similar to the renormalization that's in van der Waals repulsive term. And you can see that it's going to give you a recursion relationship, a Taylor series. We have another one here. This Y quantity is right here. I highlighted it. So it's this exponential. So it's an exponential in reciprocal temperature. Beta is 1 over kT. Epsilon is your energy. In this particular case, the ESD equation, also the PC SAFT equation does this, uses as its foundation the square well spheres. And so at its basic level, what the ESD equation is telling you in the SAFT format is you take this quantity Q, which SAFT calls M, okay, it's different letters for the same thing. You multiply it by your repulsive and attractive term. So this is the complete equation of state for the square well fluid. Okay, so you just scale your spherical equation of state times this Q. Then you subtract off this quantity, which accounts for the chain connectivity. And that makes sense, right? And so this is going to reduce the, this might need to be a minus sign, it might be a typo. And so you take the free energy of detached spheres and then reduce it by subtracting off this connectivity contribution. And this log of 1 minus 1.9 eta is the same quantity that's here. And essentially what that is this G at contact for the hard sphere fluid. So this is why I say the ESD equation is self-consistent, because it's using the same result for the G at contact throughout the analysis. Whereas the CPA that Canto-Georges has worked on, and this new thing that Chapman is working on, they use a different flavor of G and an incompatible version of this chain and sphere term. Okay, so we see that this is a very compact and simple relationship, and it shouldn't be taken too seriously, but it is self-consistent. So we're going to see this 1.9. That's going to come up over and over again. That's why I've highlighted it here. When you recognize that this exponential turns into a perturbation series in reciprocal temperature, then it's easy to understand how we get the Helmholtz energy and the attractive term. We get these different perturbation contributions. The thing I hadn't actually fully appreciated until recently is when you do this expansion, you actually get a kind of you get a negative first order term or a negative second order term from this that is opposite in sign from this contribution here to the second order term, and so it actually turns around and makes it quadratic. And so if you solve that quadratic equation, you find out that the minimum in A2 is always at around 0.28 packing fraction. And the contribution never results in a positive contribution to the A2 term, because the packing fraction of 1.9 always precludes the density where quadratic term becomes positive. And so this A2 term is qualitatively correct in terms of what it should look like. So those are some of the aspects of the ESD equation, so that this, because we put the y in the denominator here, and I did it for a different reason in 1988 when we were first talking about this, because we put this y in this denominator, it leads to an infinite series. So that is, in some sense, a renormalization with respect to temperature of this infinite series. And so the ESD equation does include a renormalization with respect to temperature. And that's pretty, there are more sophisticated ways of doing that renormalization that will do a much better job in the critical region, as we'll see. So are we done yet? We might be, you could argue that, but when you compare what the ESD equation does relative to the molecular simulation results, I'd have to give up an argument that, it's not very good. So if we compare the attractive term, the ESD equation, the A1 term really, really dominates. And so this looks like it's just first order. And, the A1 term doesn't have much of a density dependence to it. And so this looks like there's not very good agreement with respect to the attractive terms. But like I said, this packing fraction of 0.28 is pretty consistent as the minimum in the ESD equation for all different chain lengths. And the detailed molecular simulation results do look qualitatively similar. But it's a stretch to say this is good simulation correspondence. But for 1990, we didn't have these simulation results, so not bad. It could have been worse. And so a couple of takeaways. One question you might have: where do these simulation results come from? And so that leads us into this discontinuous molecular dynamics and perturbation theory. And so I'll just mention at this moment that this is a way of performing a simulation so that it's basically hard spheres. And you look at the distributions of the atoms around the atoms. The A1 term turns out to be just an average of the, remember, we're only simulating the repulsive part of these chain molecules. And so they're essentially hard spheres. They're tangent hard spheres. They're not tangent hard spheres. They're fused hard spheres. So they have a bond angle of 110 degrees, like a like an alkane molecule should. Okay. Their bond length is 0.154 nanometers. Their bond, their site diameters is around 0.36. And And so 0.15 is less than 0.18, which is half of 0.36. So you can see that the fusion of these spheres, they're overlapping more than just half. Okay, so this molecular simulations takes into account all the bond lengths, the fusion, the branches, the rings, all of those kinds of things. Good news is we're just looking at alkanes here, so there's not too much branching in rings. But we are taking care of the bond angles and the fact that the dihedral angle cannot be in the cis conformation. So there's a fair amount of detail being included in that. Well, there's maybe you could argue, you know, those are just molecular simulation results. Who cares? It doesn't matter if real molecules never actually go to those kinds of packing fractions. One way to address that question is to look at the packing fraction at the melting temperature within the context of this speed MD equation, this discontinuous molecular dynamics and perturbation theory. So now we have a detailed molecular model that is characterized in terms of intermolecular potentials. The steps of those wells define the attractive potential. And we can go ahead and compute what's the highest packing fraction that these various molecules would achieve. Well, that highest packing fraction is going to be at the lowest temperature they can achieve, which is the melting temperature. And what you can see is that methane, being spherical, stops somewhere around 0.49, something slightly less than 0.49. And methane's not really spherical, remember, it's got those little hydrogen bumps in it. But it still can't get past 0.49. So that would be the highest packing fraction that we would want to deal with for methane. But it gets more complicated as the molecules go up. You might realize, you might remember that propane has the lowest, one of the lowest, I'm 100% sure it's the lowest, melting temperatures in reduced coordinates, right? So if you divide the melting temperature by the 370 degrees Celsius, Kelvin, that the propane's critical temperature, that number comes out to be about 0.25 or 0.26. And so that's a really low reduced temperature at which this melting finally freezes. And so I thought probably propane is going to have the highest packing fraction at the melting temperature, but that was not true. Branching also frustrates the packing. And so when we get to 3-ethyl heptane, we get to the highest packing fraction that I've found. Okay, so this is the ultimate packing fraction of interest. But remember, there might be some other situations where you mix ethyl heptane with something else, and that frustrates the packing even more. So we might need to go to even higher packing fraction. So let's keep an open mind about that. So let's see if we can change our divisor here of 1.9 so that we can get to a packing fraction instead of 0.53, we'll get to 0.63. Or maybe we'll make this 1.5 and go to 0.67. So let's treat that, let's keep an open mind about what that number should be in order to best represent the molecular simulation results and then still achieve a reasonable equation of state. And so you can see we've got pretty good representation of the molecular simulation results. Now we just keep the ESD attractive term. Are we done? Well, that doesn't look too good. Okay, so that doesn't agree. So the A naught term or the Z naught term is okay now, but the A1 term seems like we could do better than that. So well, I'd say we're not done yet. Let's take a look and see if we can still avoid artifacts and still get the A1 term right. And so here what I'm showing to you is that there's only one van der Waals loop. And unlike the PC SAFT equation, there's no intermediate density. We're pulling the liquid density off of that highest packing fraction root. Another thing is at 1 Kelvin, okay, so I've set a goal. I'm not going to go below 1 Kelvin in terms of my applications or my evaluation of whether this thing is artifact free. So if it's artifact free at 1 Kelvin, it's artifact free to me. And so you can see that this slightly adjusted ESD equation is artifact free. So it doesn't need to be cubic when we apply the Carnahan-Starling equation for the hard sphere contribution. We can do that. What about the A1 term? Can we do a little bit better in that regard? Well, in this paper, we analyzed what the A1 contribution should look like in order to match experimental results and simulation results. And it turns out the derivative behavior is very critical. And so you need to include terms that aren't polynomial terms that disappear when you differentiate. And so this is the form that we came up with that was capable of getting the derivative properties right, because derivative properties are very, very important in thermodynamics. We can visualize how the second derivative with respect to energy is the heat capacity. Second derivative with respect to first derivative with respect to density is the pressure. Second derivative is the compressibility. And so all of those properties are important. So let's see if we can improve this and still avoid artifacts. Oh, there's a slide missing. Well, there's a slide missing, but it's pretty simple. It shows, yes. Oh, okay, here it is. Okay, so yes, I took this this functional form, applied it to the simulation results, and got these blue curves. Okay, so these blue curves here represent the simulation results accurately, pretty accurately. There's a little bit of deviation here for butane. And this blue curve corresponds to that blue curve. So there is no artifact. Okay, so this is the slide that shows us we don't need a cubic for the repulsive term. We don't need a cubic for the attractive term. We can still get the A1 term right. We can get the A0 term right. So are we done? No, because the A2 term isn't right yet. Can we improve that? And so what I did was I fit the points to this blue curve again, okay, using this functional form. And what you see is we get a good representation of the molecular simulation results now. But at 4.4 kelvins, I start to see this extra bump in here, this extra van der Waals loop. And when I get to 1 Kelvin, I can't avoid it. And so why is that happening? The reason is because this contribution looks the way that it does. It comes down, has this deep well, okay, at a packing fraction around 0.13. And then it turns around and goes back. So that's a problem. And it inherently leads to this kind of derivative behavior in the pressure that generates a second van der Waals loop. The reason for this dip to occur has a very clear physical reason. If you think about the packing fraction of 0.13, if you've ever done any of these calculations for equations of state, looking at the critical density, that 0.13 is pretty close to the critical density. And there's a physical reason for that, because this A2 term, I told you before that the A1 term is looking at the average distribution of atoms around atoms and computing the energy of that for the purely repulsive reference fluid. Well, the A2 term is looking essentially at the standard deviation, or the variance of the molecules around that mean, okay? And so first order term is the mean, the average. The second order term is the variance around that mean. And in since Einstein actually coined this phrase, he referred to that variance term instead of statistically as a variance. He called it a fluctuation term. And so this contribution, A2, is essentially looking at the fluctuations of molecules around each other. And where are the fluctuations maximized? At the critical point. And hopefully you recognize why that is. And so it makes perfect sense then that our fluctuation term has its maximum magnitude at the critical density. So even though it's just there's no temperature in this A2 term, it's interesting that its maximum magnitude is at the critical density, which is where the fluctuations are highest. And that goes together physically. And if you don't see that, you should try to understand what's built into your theory that is giving you fluctuations that don't look like this. Because the only place the fluctuations should really be a maximum is at the critical density. We know physically why that is. And there are other theories out there that will show you different behaviors. And we might want to talk about that. Okay, so if we want to include the A2 term, how can we do that? Essentially, we can deviate further and further from the simulation results, and then we will reach a compromise. Okay, essentially that's the only way. And so this is the best I could do. It still has its van der Waals loop here at 1 Kelvin. It's doing something weird and going all the way to infinity really quickly. But at least at 2.2 Kelvin, it's not crossing the x-axis. Okay, so we have to sacrifice accuracy with respect to the A2 term if we want to avoid the artifacts at 1 Kelvin. So what was that? 40 minutes, okay? So that was a long 20 minutes. And so it brings me to the conclusion and a stopping point where I think I could answer questions, and then we'll decide where we want to go from there. And if we want to have another meeting later and people who are interested can dial us in next time. And I'm totally open to anything that everybody might be interested in. A couple of things. Oh, one last thing I wanted to point out. These are molecular simulations of the Lennard-Jones spheres at conditions that are inside that van der Waals loop. And so what I wanted to show you is that the molecular simulations show that if you get down to a low enough temperature of 0.7 T star, which is about 0.5 reduced temperature, you do start to see this kind of waviness in your van der Waals loop. And so it's not unreasonable to see some waviness. But these curves should not be so wavy that they go up and cross the x-axis again. So that's something to think about, that the A2 term that we observe is kind of being reflected in this waviness. And what about the A3 term? We should think about that. So let me leave it there and see what questions you might have.
Thank you, Elliott. We can go for questions. We have 62 attend your seminar. It's a nice number.
Should I stop my share?
No, don't need. Who wants to? You can question more related or not. So you can, or if you want to prepare a question in Portuguese, you can do, and we can translate. So. I wonder why you are worried about 4 Kelvin in your calculation, because for me, for engineering point of view, 4 Kelvin is very low temperature. And even well, 50 kelvins for molecule like 30 bits. So it's 50 kelvin is very low temperature as well. I think that's for the constants, but even though it's a good compromise, even because we're never going to reach this temperature in chemical engineering. So
okay, never say never. Okay.
no, yeah, yeah, sure.
Okay, so let me give a little background. So one of the things that I'm doing in my efforts with the properties of gases and liquids. Okay, so let me sort of outline what that is. That's a book that's about comparing all the theories in the world to all the data in the world. And so when it comes to all the various theories and equations that engineers use, somebody needs to sort out which theory is actually the one that matches the data the best. And there are hundreds of theories that have come up in the last 20 years, maybe thousands. Every time somebody publishes a paper, they say, my theory is the best.
Yeah.
But they can't all be right. And so somebody needs to sort out, compare all the data to all the theories and see which theory is actually the best. And the people in NIST in Colorado, Boulder, Colorado, they have all the data in the world. There's another group in Germany, Gemaling's group, they also have all the data in the world. And so by going to Boulder, Colorado, I can get all the data in the world and half the problem is solved. Another part of that equation is to make Vladimir Dickey the co-author, okay? So he is my connection then at NIST. And so when I go to Boulder and start talking to people about these things, the first thing they ask me is, what about artifacts at 1 Kelvin? What about helium?
Yeah, yeah.
And
Okay.
because they evidently, they get a lot of questions about that. The history of the NIST Boulder facility was it was started when they were doing hydrogen production and deuterium production for the hydrogen bomb, I think, or something related to the nuclear bomb. And so they were always very interested in those kinds of very low temperature cryogenic applications. And so I'll just give you one more example. Propane, okay, so its melting temperature is 85, but if you were to throw in a little bit of ethyl heptane in there and you get a eutectic point, you know, you could be dealing with something that is around 50 Kelvin. But I would argue that you may be right. I mean, if 50 Kelvin, if we could set that as a baseline, then we could do so much better, okay? And you can see that with this really good reproduction of the molecular simulation results, we can go to 38 Kelvin, even with an N-alkane as long as C30. And that might be good enough to satisfy the eutectics, any eutectics that might occur with propane and everything else like that. And then you could argue, well, helium, hydrogen, are we really working in a range where we've got 99% helium and any appreciable amount of liquid propane?
What I wonder is at this temperature, you may have quantum effect. So you calculate some kind of classical mean field, but maybe the problem is this region is not by the classical constants, but either maybe more important is quantum effect.
Yeah, that's possible. But I mean, if we're going to put this in a process simulator, I think running a quantum simulation is going to be even slower. So we're going to need some sort of semi-classical characterization of what's going on there. I can say that there's another topic that I've been working on lately, that developing that kind of classical equation state for helium, and I've done it. And the trick with helium is to get that acentric factor that's like negative 0.36. So nothing else has an acentric factor like that, nothing I know of. And so what do you have to change about your equation of state to be able to make that true? Essentially, long story short, you have to make the helium soft. And
Yeah.
so instead of a 12.6 potential, if you use a 9.6 potential, you can achieve that acentric factor. So we can model the helium within a classical framework without the quantum effects. I'm not saying that that's the most accurate, physically accurate representation of what's going on, but it's what could work for a process simulator.
Yeah. My other question is about the wave. I haven't seen these data, the wave from molecular simulation close to the critical point. That's very amazing. I didn't know that. And my first think is about maybe the simulation is trapped in some region, non-equilibrium regions, because this situation is kind of very low temperature and inside the phase boundary, and maybe the simulation is trapped in an equilibrium situation. I don't know. You know,
right. Well, what I would say about this is remember, this is the NIST Standard Reference Simulation Database. So
yeah.
if you Google that, it's standard.
Yeah. Yeah.
The other thing I would mention is that Arrington is
I know Arrington.
Good guy.
I know. Very good.
Molecular simulation methods, and I don't think he would put his name on something if he didn't believe it.
Yeah.
And this translation, his argument, I think, would be, I don't want to put words in his mouth. His argument would be is that this transition matrix Monte Carlo simulation method has the ability, because it's a density of states method, sort of, it has the ability to sample those kinds of thermodynamics without running into metastability and those kinds of influences that we would normally worry about inside the intervals loop.
It's nice. People, questions?
Professor Elliott, just out of curiosity, Professor Fred mentioned about the low temperatures. I was wondering if there is any personal preference or any specific reason for using degrees Kelvin and not Kelvin. Just a.
Oh, sorry. The proper term is kelvins. I should be saying kelvins, not degrees Kelvin.
Oh, I was wondering if there was any specific reason. Maybe I was
just
wrong all this time.
Elliot, it's Gabriel here. I have a
question.
Hey,
Gabriel.
Hey, regarding artifacts and this kind of systems, because we tend much to look into equations of state to represent n alkanes, which we do know that we are interested mainly in the vapor-liquid critical point. However, when we do molecular simulations and we input some soft core repulsion into the molecule, into our model, sometimes it tends to exhibit liquid-liquid critical points in its stable liquid-liquid critical points. And these kind of potentials, which exhibit some soft core repulsion, are somewhat common to represent colloid systems. And I was wondering if maybe these artifacts could not be interesting to, not to eliminate them, but to use them in this kind of systems.
Yeah, I was thinking about, there's something, I think it's called the EVLO potential that's used for colloids.
Yes.
And one of the things that's interesting about it is it has two minima in the potential. It actually comes down to a minimum, goes up to a maximum that I think is actually positive. In other words, it's repulsive. Then it comes down to a minimum again, and then goes off to zero. And so you have these two regions where the molecules can aggregate and be at the minimum of the potential well. So my first reaction to that was, well, that sounds perfect for a step potential, right? Because we'll have a
yes.
3 steps, one down, one up, one down. And we can analyze all of those thermodynamics with simulations that are already done. So yeah, it would be super fast to map out those phase diagrams for all sorts of different depths of the potential wells, and just see what do those phase diagrams look like. So that was one thought about the colloids. I wonder. So there are different kinds of colloidal particles. Some of them have actually been modeled fairly well with a simple spherical square well model. And the reasoning there is, think about a buckyball. So this is a Buckminster fullerene, this spherical 60 carbon that looks like a soccer ball.
Yes.
And so essentially benzene rings that are all tied together in a sphere so that they look like a soccer ball. Let's think about what is the width. So let's take a 1.5 for our width of the square well fluid. That's what most people do.
Okay.
And let's say 0.36 is the sigma, the diameter of your molecular site. Okay. So 1.5 times 0.36. Well, what we can say is it's only the 0.5, that outer layer, that represents the attraction. Okay.
Yes.
Half of 0.36 is 0.18. So 0.18 nanometers is the breadth of the attractive region in the molecular model that reasonably describes benzene. I've done those calculations with benzene, and I can show you a square well benzene that does a pretty good job for benzene. And so now let's wrap those benzene molecules into a sphere and call it a buckyball. Now we've still got the width, the breadth of that layer of attraction is still 0.18 nanometers. But how big is the buckyball? The buckyball is now 1 nanometer. And so we put the 0.18 on there, and the breadth of our attractive range is going to be well characterized then by a 1.18 square well fluid wrapped around this spherical buckyball.
Okay.
And then let's think about how soft that buckyball is going to be. What we've got is a lot of carbon atoms that are fused together. So remember, a benzene, an aromatic bond is even shorter than the 0.154. So the amount of fusion and overlap of those carbon atoms is much more dense even than it is in the N-alkenes.
Yes.
And so each one of those overlaps of that repulsive core generates more overlap, more repulsion. So you can think of that as cooperative repulsion. So that buckyball is very cooperatively repulsed.
Yes.
It is super, super hard. There's nothing soft about that buckyball.
Yes, okay.
And it's going to have a very short attractive range like that. And there's something called the Giri-Falco potential that has been developed to characterize buckyballs. And if you look at it, what it looks like is square well fluid with a breadth of about 1.18 nanometers. And then of course they smeared out the attraction. So instead of being a really infinitely steep attraction, it's a pretty steep attraction.
Yeah.
So,
okay,
so that's my perspective on at least that colloidal particle that they call buckyballs.
Yes, thank you. You answered me the question, and I have just another question, if you allow me. There was some sort of buzz, I think, for the last years about a liquid critical point, even for pure components, mainly in water, the high density and low density water equilibrium. And what do you think about it, and artifacts and SAFT showing 2 to 3 critical points? Wouldn't that be something that we should maybe think about?
Maybe that's what this is. So maybe this these loops that are appearing here, and like I've argued, that I believe this is the right functional behavior of what the second order term should look like, okay?
Yes.
And so if that's always laying in the background, then maybe it's actually bigger than I've estimated. Maybe we're kicking into those liquid-liquid regions here sooner than at higher temperatures, in other words. Or maybe there's some connection between the association term, which I haven't talked about too much yet, but I'd love to talk about hydrogen bonding. And so maybe there's actually some sort of correlation between those two effects, the association effect and this A2 term, that is leading to that high density or extra liquid-liquid behavior.
Okay, thank you.
Good question, thank you.
Yeah, I expect that for liquid-liquid, the second critical point come from kind of showed potential. You need to have to a level of repulsion in order to have the second critical point. I think so. At least that's what is people simulating in physics.
Yeah, well, I kind of feel like what you need is some reason why the density, so to get the density anomaly right, you need to have some reason why the density goes down below that, what is it, 2 degrees Celsius or so. And so we have a pretty good idea that it's got something to do with the transition to tetrahedral bonding in the hydrogen bonding water. Okay, so I think so it's not, you could generate a repulsion that would make that density go down in an artificial way, but I don't think that's really what's going on. My latest thinking on this is that the transition is occurring from being 3 hydrogen bonds per water to 4 hydrogen bonds per water. And the best way to go about modeling that would be to have your hydrogen bonds be tetrahedral. But for your, and they would have to be explicit, separated from the point charges, because the point charges are just going to give you kind of smeared out interactions. And so what you need is something that is got that, the point charges, so you need 3 point charges. You need the 2 hydrogens, and then you need one kind of big sloppy.
Hello? Fred, acho que seu microfone está atrapalhando. I think you are... Yuri, please.
Oh, that's better. Thanks. Okay. Yeah. So if you put a big negative point charge and keep it far from the surface, okay. If you put the point charges too close to the surface, they're going to start to mimic the hydrogen bonds. But if you bury the point charges, then they're just going to radiate out this kind of electrical field without directly drawing in the hydrogen bonds. And then you represent those hydrogen bonds by something like a Wertheim blister potential, okay? So the blister potentials are going to give you the tetrahedral 4 bonds, okay? And the point charges are going to give you this essentially 3 bonds orientation. And then as you get, if you tune all of that just right, then what you're going to see is as we get to that 2 degrees Celsius, we're going to switch over from the point where the electrostatic charges are sort of driving the packing to where they're close enough packed that the tetrahedral forces start to take over, and we switch into that 4 bonds per water.
I agree for water. I think it's all right for water, but even for a very simple molecule, like a spherical molecule, you may have 2 critical points if you have two repulsive contribution, you know, like shoulder potential.
A shoulder potential, you mean?
Yeah, shoulder potential.
Yeah.
I don't know if you know Eugene Stanley from Boston, physicist from Boston University. He showed that if you have shoulder potential, you may have a double critical point.
Yeah. Hey, I'm a big fan of shoulder potentials. Those can be modeled with step fluids. So, yeah.
For you, it's very easy to simulate this.
Yeah. So in fact, that's sort of fundamental. One of the ways that we achieve high packing for our simulations of the DMD is we essentially impose a shoulder in our repulsive part, and so we make our sigma. We impose another sigma that's at, let's say, 0.3 nanometers, okay, instead of 0.36. Then we have no problem packing those, okay? Then what we do is we run a little simulation where we keep moving the height of that shoulder higher and higher and higher until we get it to infinity, and we get all of the molecules de-overlapped. So running a simulation or building the theory with a shoulder potential, that's just good fun for me. I'd be happy to do that.
I think with your prisma and with shoulder potential, you can see the double critical point.
Maybe, but let me wonder, you know, how realistic is that for a molecule like argon? Do we really believe that there's going to be that kind of behavior for argon, or is it going to be more like the van der Waals loop that I've talked about with the artifact-free approach? Maybe a way to answer that is to look at the interfacial properties.
Don't know.
I would bet that I could get good surface tensions with a simple van der Waals loop. And that an LLE behavior in there, somebody who showed me that, let's say I got a journal article to review, and they said, oh, there's going to be this liquid-liquid phase behavior inside there for the for argon. I would say, okay, show me the surface tension from that. Does that agree with the observed surface tension for argon? I would want to know that before I say that's a good idea.
Interesting discussion. See if people want to question something. Do we have more questions, please?
Oh, I have a question. Professor, I would like to know a little bit more about the DFT strategy that you used to model the interface. I know it's probably not the focus of your work, but was it based on SAFT strategy or something like PC SAFT DFT?
So actually, I'm couldn't be more excited about this theory, and so it's just that this student graduated, and so I haven't gotten back to it for a while. Yeah, so if you have an interest in that, I'd love to talk about it. So, so this paper here, what we did was we laid out a theory that's called SAFT gamma, and then we used what we call the WCA perspective. So the SAFT gamma theory is what the George Jackson group has been using for many, many years. And what I like about it is that it provides a basis, a framework for fused spheres. The irony of that is that the direction that the George Jackson group has gone now is to tangent spheres. So their SAFT VR models are all for tangent spheres. So you might assume that their theory only works for tangent spheres, but the SAFT gamma originally conceived was actually the whole reason for it was because it could treat fused spheres. And so that's what we liked about it. So you have a kind of an extra parameter in there and a way to adjust things so that you can use that equation of state approach to represent your real molecules. okay, with few spheres and everything, and then use that equation of state approach to exactly characterize the molecular simulation results in all their details. And so coming from that speed MD approach, where we were able to treat all the branching, rings, and fusion of real molecules, I didn't want to throw that away when I went to continuous potentials, right? You don't want to try to get more sophisticated and then throw out all the good details that you had before. So I want to keep all of the branching and rings and fusion, bond angles, keep all of that right, but still have an equation of state that can represent the molecular simulations and everything accurately. And so that's what the SAFT gamma WCA theory is. And so then in this series of papers, I think this might actually be paper 1, and paper 3 came out in, maybe I'm mixing up the years, maybe paper 1 came out in 2013 and paper 3 came out in 2014. Probably that's what it was. But anyway, there's 3 papers like this, and I think this is the 3rd paper where we show how you build up all of this knowledge systematically, and you can characterize all your molecular simulation results for nonpolar fluids, then polar fluids, and then associating fluids, and then interfaces. And so there's a complete framework that sort of lies in the background of this paper, of this picture here. And so that's sort of the way I would approach it. And it does include SAFT. And let me just sort of, I touched on this, but I'll come back to it. Yeah, right here. So you remember how I told you that the A2 term should have a minimum, or should have its maximum magnitude at the critical density. Now this is rho sigma instead of packing fraction. Rho sigma is about double packing fraction. And so you can see this is going to be about 0.25 or something like that instead of 0.13. So it's still got its maximum magnitude at the critical density when you use the WCA split. Do you know what that is? The Weeks-Chandler-Anderson split?
Actually not.
Oh, boy, I
WCA.
don't know if I have a graph here. Okay, so imagine a Leonard-Jones force field. Oh, I'll bet, let's see. Yeah, okay. So see if I can draw on the screen like this. So with my finger. Okay. Okay. So here's a Leonard-Jones potential. All right. So what Barker and Henderson, and here's 0, right?
Okay.
All right. So what Barker and Henderson do is they say, all right, let's draw a vertical line right here where the potential crosses 0. And what's left of that line, we're going to call the repulsive part of the potential. And what's to the right of that line is the attractive part of the potential.
Oh, okay. I got it.
Okay. What WCA, what Weeks, Chandler, and Anderson did was they said, no, we should draw the line at the minimum of the potential and then add epsilon to it. Okay. And then what's to the left of the line with the plus epsilon on it, it's going to be a little bit smooth at the bottom, right? It's going to reach a flat spot at the bottom where the minimum is 0. And then it's going to go to infinity to the left of that line. And that should be the right repulsive potential.
Okay, I agree.
Okay. So why should these 2 different potentials give these different results that are illustrated here in this graph? This is a good quiz question for you. This is a brain teaser for everybody. All right. Whoever yells out the answer first wins. So what we see is that when we use the Barker-Henderson split, we get these results that George Jackson likes. Okay. When we use the WCA split, we get the behavior that I argue ought to be the right behavior. But let me just say at the outset, they're both technically right. These are the results that the simulation will give you. There's nothing wrong with the simulation. But in the case of the Barker-Henderson split, you're going up to higher and higher densities, and your fluctuation term is getting larger and larger. How can that happen? Because as you go to higher and higher densities, the molecules are getting more and more packed, right? They can't move around.
Yes.
So the molecules can't fluctuate, but your fluctuation term is getting bigger and bigger.
It doesn't make sense at all.
That's because it's my explanation, right? If George Jackson was here, you know, he might convince you the other way. But there is a physical reason why this is happening, and it relates to this picture over here.
Oh, okay. Okay. Now I got it.
Oh, what is it?
Well, I really don't know.
Don't be shy. Don't be shy.
WCA.
Oh, you're saying you got it. You got the question.
Yeah, I got the question, not the answer.
I thought you got the answer.
I got the problem, not the answer.
Oh, okay.
But what is the answer? I'm curious about it.
Well, let me give you another little hint. Let's see, URES. That's my horrible handwriting. With my finger, okay? So in the speed MD equation, remember, the A naught term is independent of temperature, right? We're imagining a perfectly repulsive reference contribution.
Okay.
And so the A naught term has no temperature in it, and the internal energy is the derivative with respect to temperature of the Helmholtz energy, and so the A naught term goes away when we take the derivative to get U, right? So it's just going to be equal to A1 over T plus 2 times A2 over T squared, right? And that 2 comes from taking the derivative of the T squared in the expansion of the Helmholtz energy, right?
Right.
So it's a polynomial derivative. All right, so so now what do you think's happening with the energy in the Barker-Henderson split that's not happening in the WCA split? So maybe I should draw a picture of what the attractive part of the WCA split looks like. Do you see those little dotted lines down here?
Yes, I do.
Okay, so because the repulsive split adds the epsilon, right? When you're going to add your repulsive and attraction and get back the original, then the attractive part must have this flat negative epsilon down here, right? So the attractive part is negative, negative, negative epsilon, and then it goes smoothly up into 0.
Right.
Get any ideas yet?
Not yet. Somebody help me, please.
Well, one thing that we know is that the speed MD A2 terms, they all look like this. They don't have any extra shoulder coming out up here.
Yeah.
Let me give you another hint.
Please.
Let's draw A2 for square well spheres. And so it's kind of upside down, right? This is 0, all right? What it does is it comes down here, and it goes like this, and it kind of goes like that. If it's a wider well, it goes like that. And then it comes down like this. So the A2 for square well spheres, okay, it also shows what I call a shoulder, okay, a high density shoulder. Think about square well spheres. What does that potential look like? And why would we have a shoulder here in your A2 contribution? And why does that relate to your internal energy? Why did I want you to think about that?
Okay, let me think about it. If somebody else has the answer, please help me while I'm thinking about it. Well, A2 has this shoulder behavior. How about A1? How does it
A1
look
is
like?
perfectly smooth, just like that.
Okay.
It's only occurring in the fluctuation term, this shoulder.
Okay, I think I'll give up. I don't
All
want
right,
to
let me
give
explain.
the correct answer. I don't
I'll give you the answer for the square well spheres, and then see if you can figure out the answer for the Leonard-Jones with the BH split.
Okay. Okay.
So remember that your square well potential is very sharp, right in here. Okay, right at this position, the potential energy is changing. And so if you read my thermo book, you'll see that we use the little u versus r to describe the potential energy between molecules. And then there's something called the energy equation that says the big U is equal to rho over 2 times the integral of G, the radial distribution function, times U, the little u, times 4 pi r squared. It's not easy to do this. Dr. Have you heard of the radial distribution function before?
Yeah, that's a do.
Okay, good. So if you think about that, that says that this big U is a weighted average of the little u, right? And so
Right.
the radial distribution function is just the weighting factor. Well, the radial distribution function times the density. So you could say the pair density, the local density, is the weighting factor for this molecular energy.
Right.
And so, in fact, now this G is the total G including attractive forces. If I make that a G naught, then this is that U1 term, which is exactly the A1 term. Okay, so now you can see how the A1 term is really just an average, because it really is a weighted average using the radial distribution function of the hard reference fluid as the basis, and then just integrating over all distances. Okay, so the little u connects us to the big U. And so if there's something about the little u that generates a sensitivity to fluctuations, then the molecules don't have to be moving very much. So the G could be smooth. But the U, if it's a sharp change and you've got molecules going back and forth, even if it's just a few molecules moving back and forth across this infinite potential, a little bit of motion in the molecules can give you a very large fluctuation in the energy.
Right.
That makes sense now?
Yes.
Okay, so that's the key. That a little bit of fluctuation in the molecules can be amplified and give you a lot of fluctuation in your A2, or give you a large magnitude for A2, even if the molecules aren't moving very much.
So these fluctuations can impact little u and also G?
Right. So we could expand G as a perturbation series in temperature also. So we could have a G naught plus a G1 times beta epsilon plus G2 times beta epsilon. So okay, the G1 would give me A2. that's a little confusing.
Okay.
I think we are.
You're gonna call time out? All right.
Yeah. No. Okay. Okay.
So
Fred, just one quick question. Just to finalize the rationale in this explanation.
Okay.
Professor Elliott, if you would have no splitting at all of the Lennard-Jones potential, then you would have a behavior similar to the black square, or
there is no, you can't analyze the perturbation contributions without a split. So what we're essentially doing is we're dissecting this Helmholtz energy into its individual components with respect to temperature.
Okay.
That's what the perturbation analysis enables us to do.
Okay.
Still thinking about it.
So maybe I also didn't get the complete picture, but yes, thank you for your time and for your beautiful talk.
Okay, let me answer this question then that I posed. And I asked you to think about it. Sometimes if you're just sitting there and I'm explaining things, you fall asleep, all right? But if you got to think about it, then maybe you don't fall asleep, okay? So, but at the same time, I don't want you to stay awake all night thinking about this. So let me just tell you. Okay, so what's happening with the Barker-Henderson split, you still have this very steep rise in the potential function, right? And that is, although it's on the other side of the potential function, it's still a very steep rise in the potential function, analogous to the square well rise that's giving rise to this square well shoulder, okay? So with the Barker-Henderson split, you have this steep rise. And think about what you're doing as you go to higher and higher density. You're packing more and more molecules close together. Well, where are they when they're close together? They're right here. You're putting more and more molecules right here where where any variation in the molecular packing gives you a huge value in your fluctuations for A2. But in the WCA split, it's just flat there. So motions of the molecule don't change the energy at all as you go to high density.
And that's why it's a shoulder.
So that's why there's a shoulder for the Barker-Henderson split.
Oh, okay. Now I got it.
That's why we're getting this behavior for the Barker-Henderson split and no behavior for the WCA split, because the molecules just aren't moving much anymore. And if they're not moving much, actually they can move a bit, and there's nothing happening here, okay? Because we're packing all the molecules into this very close range where there's nothing happening with respect to the potential function. Nothing happening with respect to the energy. It's just going up. More energy means more packing of the molecules. So, but that's going to be reflected in the A1 term, not the A2 term.
Oh, I think now I got the explanation, not the question. Thank you, Professor Elliott.
Okay.
Thank
that
you.
was a good brain teaser.
I think it was a little bit longer than we expect, but was very nice, and I thank you very much. I think we can maybe schedule another to continue this seminar if you want to. That's for us. It's going to be very nice.
Sure. Nothing I'd like more.
Okay. So thank you very much.
Yeah, we'll email. We'll and maybe you can survey the students and ask them, any topics that they'd like to hear more about. Maybe the SAFT gamma theory. I didn't talk about the Gaussian extrapolation. So that's a renormalization that has a big impact around the critical point. And I didn't talk about the virial coefficients and the way that we can unify thermodynamic perturbation theory with virial coefficient analysis and get a kind of a unified theory that represents all densities and temperatures with a high degree of accuracy, even around the critical points.
Okay, thank you.
Okay, so keep in touch and let me know what's interesting.
Okay, bye bye. Thank you.
Thank you, Professor Elliott. Thank you very much.